start, and I'm CEO and CTO of FlashGrid. And today we are going to talk about how you can take really large Oracle databases and put them on AWS cloud. Short disclaimer, some of this information is preliminary, so if you have a specific project, specific requirements, we'll need to discuss them with you in a little bit more detail, so please keep that in mind. Now, let's say you have a database that is larger than 100 terabytes. So why not just put it on AWS? What are the obstacles there? Well, let's first see what are your options. The first option is Amazon RDS service, which is a database as a service, as probably many of you already know, which makes lives of DBAs usually easier. However, RDS has some restrictions. And the first one is the size of the database. Today, it's 64 terabytes max. The second restriction is that you can get the performance of a single EC2 instance out of it, which limits you by 80,000 IOs per second. And more importantly, it also limits the amount of storage throughput in terms of megabytes per second that you can get from that database. So if you have large database and you need full table scans, it's going to take a while to scan those terabytes. So these are the main limiting factors, apart from functionality, which is a separate topic. Now, the other alternative that you have is just take an EC2 instance, infrastructure service, whether VM or bare metal, and put your database straight on it, so you can manage the entire thing. In that case, you don't have a strict limit on the amount of storage that you can attach to the instance. You can attach multiple EBS volumes, and those volumes can be large. So you can get those hundreds of terabytes if you need to. However, you are still limited by the same performance. So same 80,000 IOs per second and same less than 2 gigabytes per second of storage throughput. And on top of that, you also need to now think of how do I build my own high availability, because usually the large databases are also important databases. So these are the two challenges that you have, that you might be facing if you need to move a large database to AWS. By the way, if there are any questions along the way, please feel free to ask. We'll try to be short, quick with answers, but don't have to hold them until the end. Now, what changes today is that there are some new instance types available from Amazon. They've been available for a few months already. Most importantly, those are i3EN metal and IR5N metal. So these are the bare metal instances that have, most importantly, 100 gigabit per second Ethernet network connectivity. So that allows us to use all that throughput through the network. And second, on the i3EN metal, you also have 60 terabytes of locally attached NVMe SSD storage that provides up to 16 gigabytes per second of throughput and up to 2 million IOPS per instance. But 60 terabytes is still not what we're looking for. We want, say, 100 or more terabytes. And also, those local, if you use those local SSDs, they are not persistent. If you read Amazon's guides, they tell you, don't put your important data on those SSDs. They are ephemeral. So what do we do about it? Well, first, we can pool multiple instances together so that we can get larger capacities. And whether those are those local SSDs or EBS volumes that are attached to individual instances, you can have multiple of those instances pooled together. And that gives us, well, first, larger capacity, and second, we get the aggregate throughput of all those instances. And second, we also need to add high availability and persistency to that storage, right? You don't want the data to go away, or even if it doesn't go away completely, you don't want your database to be disrupted just because you have, let's say, 6 EC2 instances running, and well, one of them has a glitch. It's like 6 times higher chance of having a glitch, and you don't want to increase your chances of having a glitch in your database by the factor of 6. And if you care about uptime, then you probably also need rack to be running as your database engine to maintain high availability. Well, let me do a quick intro of our product, SkyCluster, and just to explain what it is, and then I'll go into details of how we achieve all those capacity and performance targets using the SkyCluster. So what is SkyCluster? First of all, it's a high availability database system that runs on EC2. It does use Oracle RAC database engine, although in some cases you don't have to use it, but if you need HA, you can use Oracle RAC. It also has a choice of, or provides the flexibility of choosing between different types of storage, EBS or local SSDs, or a combination of the two. And importantly, it's infrastructure as code approach, so you can deploy these multiple instances all pooled together and connected in a single cluster in a form of a template that is deployed to your infrastructure as service account. So it is makes it the process very repeatable and fully automated, easy to deal with. Now let's consider specific cases where we want to have a large database. Depending on the specific requirements, we'll just look at various different types of architectures that can meet those requirements. The first case is the simplest one. So let's assume you don't care all that much about super high availability, but you still have this large database and you need a lot of storage throughput. And actually, it's I added this slide just today because we actually are talking to a customer who is interested in this particular case. So it is actually pretty simple. We have one database server running on R5 N-metal instance type. Again, has 100 gigabits per second network. And we have 5 or potentially even more storage servers. And those storage servers have EBS, general purpose SSD volumes attached to them. So in this case, the storage throughput of these 5 storage servers is aggregated, and effectively we're only limited by the network throughput that the database server has, because we can always add more storage servers if we need to. So 100 gigabit per second gives us roughly 10 gigabytes per second of storage throughput. And also, like in the configuration that is shown here with 5 storage servers, if you remember, each instance has the limit of 80,000 IOPS per second, so 80,000 times 5, 4,000 IOPS. So these are the capabilities in terms of performance, and in terms of capacity, well, we can have as much as you want effectively, because just add as many GP2 EBS volumes as you need to each instance, and then you have as many of those storage servers as you need. One interesting thing here is that we do use normal redundancy disk groups, and that is for data HA. So again, if we have 5 or more of these storage servers, chances are one of them will have a failure at some point. Now the instance might reboot. You don't want your database to stop at that point. So what normal redundancy disk group gives us is it's basically a two-way mirroring done by Oracle ASM. And I assume most of you know what Oracle ASM is. And it allows us to lose any of these volumes, or even an entire storage server, without losing access to data, because there are always, each block has 2 copies of across 2 different storage servers. For those of you who are familiar with Exadata architecture, this actually looks somewhat similar, right? Except that we have only one database server, and these are storage servers called storage cells in case of Exadata. So each of these storage servers will be placed in a separate fail group, which is an ASM concept, and that tells ASM that it shouldn't put same block of, or both copies of the same block in the same fail group. It knows that it needs to spread them across 2 different fail groups. So once storage server fails, there's guarantee that that block is somewhere else on one of the other storage servers, so that your database can keep running. And when the storage server comes back up, well, the resynchronization automatically starts, so you don't have to resynchronize the entire amount of data. It's only the data that has changed during the outage of that particular server that needs to be resynchronized. So it's a relatively quick process. Any questions before we jump into more advanced cases?
So
Sure.
you're selecting 2 of those storage server groups, and so you still have only 2 fail groups in your ASM?
No,
Or do you have 5 fail groups?
5.
In each one? You have
5.
in each
Yes,
one.
5
Okay.
fail groups.
I was going to say, if you went 2 and you lost one, you'd be read-only, which would not be well.
Right, so 5 fail groups, and because it's two-way mirroring, you can lose any one of them. All right, so let's consider a more advanced case. In this case, we have rack, and so we have, instead of 1 database server, now we have 3 database servers. And also, why don't we replace those GP2 EBS volumes with local SSDs? So it looks very similar to the previous architecture. The differences are that now we have each of these database servers having 10 gigabytes per second of throughput available to it. So your maximum aggregate storage throughput is tripled or quadrupled, or whatever the number of database servers you want to use. So it kind of scales linearly with the number of database servers. And of course, you need to keep up with the storage servers as well, right? So if you want to have 3x the throughput of the at the database server level, you need to match with the throughput at the storage server level. Now, you might have noticed that says high redundancy disk group now instead of normal redundancy. And the reason for that is that local SSDs, again, are ephemeral. So we want to have extra protection. So basically what happens is that if one of these guys just reboots and because there was some kind of panic or just some intermittent failure, and it just reboots and comes back up, everything is good, just resynchronizes as before. However, if one of these guys just fails completely and it has to move to a different physical host, there will be no data here left. So in that case, we still have the data, the full copy of data on other storage servers. However, because these are local SSDs, they don't have this extra layer of built-in protection that EBS has. So we are potentially exposing ourselves to bad blocks. So again, those who use Exadata are now probably familiar with the recommendation that Oracle has that for anything critical, use high redundancy. And this is why we want to use it here. And there's even more reason to do that. The good thing here is that because we now have more storage throughput at the database tier level, we can make more use of the storage throughput that local SSDs provide. And we can use the storage servers that have also 100 gigabit per second network. So each one of these now can have 10 gigabytes per second of storage throughput. And database servers also have 10 gigabytes per second of storage throughput per node. So you can add, you can do the quick math and see how much you get. And okay, it actually says up to 7 gigabytes per second per database now. And the reason for that, I forgot about it, is that we also need to reserve some throughput for communication between the database nodes. Because now it's rack, it needs private network connectivity, it needs cache fusion traffic between the nodes. So we need to reserve some of that, the network bandwidth, for those purposes. And by the way, the segregation of these two different types of traffic is done using our software with quality of service there. So it's done properly, even though it's just single trunk from EC2 perspective, but we do take care of separating storage traffic from private network traffic from public network traffic. And because now we use high redundancy disk group, we can tolerate loss of any 2 nodes at a time. We don't want to get there, but in case it happens, it still can survive that. But now, if we're using local SSDs, we're effectively limited by the capacity of those local SSDs, because unlike EBS volumes, there's a fixed amount of local SSD capacity attached to each of those instances. So in case of 5 storage nodes, we get exactly 100 terabyte of usable capacity, because each one has 60 terabyte of raw capacity. We multiply that by 5, that's 300. But because high redundancy does triple mirroring, we divide 300 by 3, so 100 terabyte of usable capacity with 5 storage nodes. But nobody limits us in how many nodes we can put together. So we can have 300 terabytes with 15 storage nodes, for example. What if we need more capacity, but we don't want to add more storage servers, or we don't need all that capacity to be super high performance? So in that case, we can do a combination of local SSDs and EBS volumes. So we can attach EBS volumes to the same storage servers, and we'll just need to configure different disk groups. So some disk groups will have will use local SSDs, and other districts will use EBS volumes. So faster data goes on local SSDs, slower data goes on EBS volumes. Now, more sophisticated case. What if we want to spread this across availability zones, because we're really concerned about our uptime SLA, and well, it does happen that there might be an availability zone-wide outage. So, as you may know, the availability zones are effectively separate data centers, physically separate buildings, usually some 10 or 20 miles apart. So they are protecting you against some local disaster that affects one of those data centers, but they also protect you against some infrastructure failures within availability zone. So what we can do is we can spread your rack cluster across those availability zones. And well, the good thing is that even though it seems like, well, two different data centers, what about performance? Well, the throughput between availability zones is actually not limited compared to same AZ, if you structure it correctly. And also, the latency, yes, it definitely will be higher, but it's still pretty low. It's still 1 millisecond or less in most regions between most pairs of the AZs. You can even optimize it and find some pairs of AZs that are like 0.5 millisecond. And also, when we read data from the storage, we can make sure that all the reads are served from the same availability zone. They don't. So and usually the bulk of the storage traffic is reads. So we can make sure that all those reads are served from the same availability zone, so there is no extra latency, no extra charges for your inter-AZ traffic. So only the write operations or updates have to cross availability zones. And there is such concept as, which is relatively new, that appeared in GI 12.2, that is called extended redundancy disk group. So that what extended redundancy disk group does, it creates 2 or 6 copies of data. 2 or 3 copies of data per site. And site, in our case, would be an availability zone. So we'll have, let's say, 2 copies here, and 2 copies here, and we also need a small quorum server that just does arbitration between the 2, just for split brain scenario avoidance. But let's not be concerned too much about this part. So here we have effectively 4-way mirroring, 2 copies in each availability zone. And this type of setup can tolerate loss of an entire availability zone. So let's say your data center A, availability zone A goes away. Well, you still have 3 database servers running here. And of course, it doesn't have to be 3 database servers. It can be 1 or 2. It's your choice. Well, let's try to simplify it a bit. Scale it down. We can have a setup with where we have local SSDs plus EBS volumes in the same disk group. but spread them across two different fail groups. And again, you can have pretty much any number of storage servers in each of them. But what's important here is that the storage servers that have local SSDs in that particular fail group can be configured to be a preferred read target. So all your reads will be served from the local SSDs, and these guys will be used only for persistency. So in most cases, these storage servers are just writing data but not reading it. Only if there's a failure here, then the reads will be coming from here and the data here will be restored from these servers. So basically what it gives you is that most of the time you can have a very high storage read throughput, and you can configure all your read-intensive services to be running on a subset of your database servers that read from these local SSDs. And you can also have write-intensive services that are running on the other subset of your database servers, and they can be reading from these guys as well. So this is just a normal working scenario. If there are some failures and one of these guys goes away, then the services can move around and the reads can be served from here. But most of the time, you will have this really high read throughput served from the local SSDs. So in certain scenarios, this might make sense. It just helps you to do it in a more cost-efficient manner. But at the same time, you can get the really high throughput at lower cost. Yes.
Got a question regarding the read-intensive services, for example. Would you configure that during the creation of the service, or there's something you need to configure within ASM layer?
Oh, it's just a service. The concept that RAG has with service architecture. So it is basically, you create the cluster, you create the database, and then on top of the database, you configure those services. So the application that does a lot of reads will be connecting to these services that are configured to be running on these database servers that have basically reading from the local SSDs primarily.
I think it's an instance-specific parameter, so you would just point your services to those instances.
It's an instance affinity.
Right, right. So it's like preferred in basically it's preferred instance. Like this read-intensive service will be running on these particular nodes, unless as long as those nodes are available.
So you would just use servctl create service. That's
Yes.
all you need.
Yep. Sure.
Sorry. I have never put an ASM on with two Failgroups on completely different type of disks, mostly because I'm concerned that one would write really quick and be waiting for the other one to catch up. How does ASM deal with it? Is it error much on you?
Oh, yeah, we have such configurations actually in production, and it works pretty well. So yes, there is some disparity between the two types of disks, and that's why. But actually, that's the whole idea here, is that this is the persistent storage, but it's slower, and this is less persistent storage, but it is faster. So
right, ASM's going to want to write to both of them at the same time.
Exactly.
Will not commit until both are written to. So
Correct.
you are, weak lead kind of. You're as slow as your slowest service.
yes, so your writes will be as fast as the slow volumes, but your reads will be as fast as the fast SSDs, because all the reads will be served from them.
Question.
Yes.
So, with using SkyCluster, are you copying the data from the large Oracle databases and putting it in the cluster before going to the AWS? Seems like you have a full cluster you have, and it seems like you're storing the data.
Well, it's think of it as, so this is all infrastructure, and your database is just running on certain database servers, and so you can create the database in any possible way. You can just create it from scratch right there, DBCA. You can just restore it from RMN backup. You can configure DataGuard and replicate it from your on-premises database. So all those options are available to you. So it's you think of it as if you had to move from one data center to a different data center. You have Exadata here, and then you deploy another Exadata in your other data center, and you want to move everything. How would you do that? So same logic applies, no difference.
So you have data set up and you switch over to this environment?
Yes, that is correct. So a similar concept, but to the previous slide. But now we add more storage servers, and we use high redundancy. So it's a more expensive configuration, I would say, but it allows you to run, to have larger capacities and with extra redundancy. So now you can see here that we have two failed groups that use local SSDs and one that uses the EBS volumes. And so in this configuration, you can lose any two storage nodes. And simultaneously lose and still keep running. And then we can take it even further and again span it across 3 availability zones. So, it shows you that we have all that flexibility of how we structure it, how we mirror data, how we get faster versus larger. And that we also can achieve higher availability by spanning it across multiple AZs. What's interesting here now is that we take the EBS volumes and place them in a separate availability zone. So your database services in this case would be running in one of the, across the 2 main availability zones that have faster local SSDs, and in the 3rd availability zone, you don't have any database instances, just the persistent storage servers. Let's scale down a bit. Let's say we need 3 database nodes and only up to 60 terabytes of data. Well, we want it fast. In this case, we can actually implement a hyper-converged architecture where we don't need to have separate database servers and separate storage servers. We can have those local SSDs actually attached directly to the database servers. And so basically, you have high redundancy disk group, each database server, local SSDs attached to each of these 3 database servers are grouped into the same fail group. So we'll have 3 fail groups here. And plus, we also need 2 additional quorum servers, but again, it does not affect our performance or anything. It's just or cost. It's just for availability for avoiding split brain. So it's a much more compact design. As you can see, we have removed a lot of components, But as long as you're okay with up to 60 terabytes of fast local SSD storage or usable 60 terabytes, then this can be a more cost-efficient choice.
I have a question for you.
Yes.
Can I get rid of the SSDs and have all UBS?
Yes, and then it would be the very standard configuration that we have today that you can deploy in just over an hour, starting from just go to our website, a few mouse clicks, and you have that cluster. So this is a little bit more advanced. So that what you're asking about is just our very standard configuration. Yes.
Why do you have two quorum servers? Failover? I mean, the whole point of it is a voting disk, and if
Right.
you're going to have split rain.
Right, so because our storage is distributed, we cannot use external redundancy disk groups even for voting disks. We have to use high redundancy disk group, and you might remember or not, but high redundancy disk group that has voting disks in it must have at least 5 failure groups. So because we have only 3 here, we have to have 2 additional quorum fail groups. And they don't have any user data on them. It's
Right,
just
just a voting
tiny, voting disks effectively. Plus, actually, even for those disk groups that do not have voting disks, it is still beneficial to have the additional quorum disks because it allows ASM to keep additional copies of ASM metadata. So it's not exactly the split brain scenario, but it's like a storage type of split brain that it can help avoid. It's less critical, but it's still beneficial, and ASM administrator's guide says that we definitely recommend having having those at least 5 failure groups for any high redundancy disk group. So let's further simplify it, or kind of try to reduce the cost here now. So let's say we still are okay with up to 60 terabytes, but we only need two database nodes. What we can do here is have the local SSDs attached only to the 2 database nodes, and we can have a third storage server with EBS volumes. So we have 2 copies on local SSDs and a third copy on EBS volumes.
What's the difference between the 2 configurations? When you have everything shared within the database servers and within one storage server?
Yeah, the difference here is, well, first, obviously you have 2 database servers instead of 3, and maybe you just don't have licenses for the third one, or you don't need it. And then it's also the persistency. So this configuration is a little bit tricky in that sense that you cannot switch these 3 database servers off completely simultaneously. If you do, you have data loss. So it's normally you wouldn't do it, but if it's some sort of a test environment, you don't want it to be running all the time, and you want to sometimes just switch it off completely, it's actually more practical to have it one persistent copy. So when you bring it back up, the entire cluster, the data will be automatically resynchronized from the EBS volumes to your local SSDs. So it is somewhat more persistent, I would say.
There's one slide, just 2 slides before,
Okay.
where we have EBS volumes shared as well. Oh no?
Yeah, it's you can mix and match in all those different combinations. The question is what actually makes sense depending on your particular requirements in terms of performance, in terms of high availability, usage scenario, cost, and capacity. So we have, if you go to our website, we have 2 very standard configurations that we offer by default. It's just 2 rec nodes and 3 rec nodes with EBS volumes. And those just like cookie cutter configurations, majority of our customers use them. If you need something more sophisticated, more advanced, more nuanced requirements, then we can help you with selecting an optimal configuration. And we just describe that configuration in a text-based config file. We just list, okay, well, these are the database nodes, these are the storage nodes, and this is how what types of disks they're attached to each one of them. And you still can easily deploy it, but we do need to put some thought into how you structure it.
So when you switch off the tools, the servers in this case, it's more safe.
Yes, in this
There's
case,
no data loss, so
right.
the blocks are set in DBA's values
Right.
before the switch off.
Yes, yes. Because it's kind of funny, but one of our customers who deployed more than 20 clusters using local SSDs, they still try to, it's pretty expensive infrastructure that they have, but they still try to save money because, well, cost saving is good. So they actually try to keep one of the database nodes down when they don't need it. So in that case, it's just kind of an example where things are being used not as you would think they normally would. And it does create some interesting nuances there, but nothing special, but still need to take that into account. So in this case, if you want to switch your cluster off for a week because you're going on vacation and you don't need it, and and if you know you will need to do that every once in a while, then this configuration might be more practical. So I guess that's what I wanted to show you about the specific configurations that are possible that our SkyCluster product enables. But just to give you a bit better understanding, what is this all about? So I'd like to finish with some more background information about what SkyCluster is. I described it in just a few words, but let me just describe in a little bit more detail. Again, it's what we call the engineered cloud system, and it is delivered as in the form of templates, and they're generated automatically using our online tool for more standard configurations, or with some a little bit more manual work up front if it's more custom configuration. But in the end, you get this entire pre-configured system. And I suppose majority of you are DBA, so as a DBA, you probably care about how you manage your database, how you manage your ASM and clusterware. So we try to keep it as DBA friendly as possible. You get the standard rack environment if you choose to use rack. You get standard ASM and clusterware. You can keep using your tools such as RMAN and DataGuard and Golden Gate and Enterprise Manager. You have full control of the database features and the patching process, so it's not database as a service. It is actually fully controlled by you. The patching process is standard, just do it the way you're used to. Storage expansion is easy, especially if you use EBS volumes, or for those configurations where you use EBS volumes, you just attach additional volumes and they are exposed to ASM, and you can add those additional disks to your disk groups or create new disk groups. And importantly, our entire company is focused on the solutions for Oracle database, so we do have very deep Oracle expertise, and we can help you with just with the initial evaluation of what configuration makes more sense with sizing, performance assessment, as well as support and all the during the entire lifetime of your cluster. I already mentioned that it's you have full access to those machines and that are running this cluster, but also we do not have access to your VM. So again, we are not a managed service provider. We are not a database as a service provider. So we give you this as an appliance, and then it is in your hands and you fully control it. We can help you, of course, but it isn't under your control. So we don't have access to your systems or your data. If you're using EBS, there is an option for data encryption that is done by EBS. The local SSDs also have embedded encryption, and that's part of the reason they are ephemeral, is because they want to wipe it out if in case the tenant changes. And of course, you can also enable Oracle TD for extra layer of protection. We support database versions starting from 11.2 and all the way through the latest 19c. You have a choice of Oracle Linux 7 or Red Hat 7 as your OS. And you can choose between different VM types and sizes. We've been talking about those who that have 100 gigabit network and those local SSDs. So we talked about specifically 2 instance types. But in reality, there are many more, and there are some bare metal instances that have 224 CPU cores, so really big ones. And so you can consolidate sometimes. We talk to customers who have 8-node clusters or 16-node clusters, and they ask us, okay, how do we bring them onto AWS? And well, the answer is, you don't necessarily have to have the same number of nodes in AWS, because you can use just larger instances. Because they are available today while they were not available a few years ago when you were deploying your older systems. And this is available in AWS Commercial Cloud as well as Government Cloud. An important point about our support coverage. So we do provide 24/7 support, which is important because if it's a mission-critical system, you probably want to have good support if something goes wrong. And importantly, it covers not just our software that is an integral part of the solution, but actually the entire infrastructure stack. So we take the responsibility for making sure that ASM and clusterware are happy, and your EC2 instances and your local SSDs or EBS volumes all work together seamlessly. And also, performance is a big question because with the cloud, you get some elasticity. You can change the size of your instances. You can easily spin up additional ones, but you don't want to pay extra, so you want to optimize. You want to have an optimal configuration. We actually are seeing a lot of customers try to run as small instances as possible to just save on not just on Oracle licenses, but also on just the Amazon charges. And sometimes it presents challenges to us because the memory sizes become too small, or the CPU power or storage throughput is no longer sufficient because they're so small. And we also help with those issues. So we can help you to draw the line where it's where it makes sense to downsize it further, or it's better to have it a larger size, so we can help you with AWR report analysis and identify where the bottlenecks are. And importantly, this is all available through AWS Marketplace. So you can, when you deploy a cluster, you actually don't have to pay us directly anything. All the charges are going through AWS. So same bill that you pay for your infrastructure. And it is really easy to bring up a cluster. If you take one of our standard configurations, like 2-node or 3-node cluster with EBS volumes, you just do it even without our involvement. We have some customers who we learned about them just by seeing reports from AWS that somebody is running the software. They didn't even talk to us. But of course, we encourage you actually to talk to us first, and so we can help you with selection of your configuration, and especially if you need something more advanced. But once we establish that configuration, you can spin it up in just over an hour. It's fully automated. If you are familiar with CloudFormation, it's template-based deployment. So we have an online tool that generates a CloudFormation template for you, and then you deploy that template to your AWS account. Importantly, not only it makes it faster to deploy, but also it's a repeatable process. You can do it multiple times, similar configurations, or you figured out, oh, I made some mistake in my configuration. I want to just redeploy it in a different configuration. That's easy. Just delete that cluster, create a new one after tweaking one parameter or two. And importantly, that also eliminates the human error from the deployment process, because if you have to configure a lot of components manually, the chances are high you will make a mistake at some point, and you don't want to make a mistake in a HA type of setup, because you may not find out that you made a mistake until something fails and your database goes down. So in this case, with SkyCluster, you get a configuration that is well, not only standardized, but is also well tested. So we put a lot of effort into testing all the components together, running through hundreds of cycles of load testing and failure injection. So you can be sure that it actually does work. So I guess that's all I had today. If anyone well, first you're welcome to ask questions, and I will be here, and I will be here till tomorrow. And of course, you can find more information on our website. Now, the more advanced things that I showed you today are not on the website yet. So this is somewhat preliminary information, but we'll be there soon. You can find more information about the SkyCluster for AWS, and also about specifically Oracle RAC in AWS. And also I want to mention that it's available. This solution is available for Azure Cloud and for Google Cloud, and we are also working towards Oracle Cloud. So thank you very much, and you have my email address, and you're welcome to send me any follow-up questions.